We're gonna talk about, I would say, most challenging or most complex subjects in this class, what we call heap vulnerability. And also, if you see modern exploitations, most of them are indeed exploit this particular type of bug. But in fact, without having the in-depth understanding of the heap, in fact, admittedly, it's extremely hard to understand because it's really about the library implementation that provide heap allocation features. And there are a lot of history behind this as well. So if you simply want to navigate the source code of malloc, it's a really daunting job. Hopefully, through these lectures and next week's tutorial, hopefully it covers some of the idea behind this heap allocator you're gonna work on. So today we are not actually talk about this tutorial, but rather I'd like to give a simple lecture on how to design heap allocator from scratch. Right? So how many people know about the signature of heap allocator or interfaces of the heap allocator? So say, so we have a two type of interface or API, you name it. So simple malloc, simply getting the size and return pointer. So pointer that point to the object or memory, you name it, inside the heap region. And if you want to free those memory region, you're gonna just provide the pointer to the free. And what will be the return value of the free? In fact, there's no return value of the free. So we assume as an API, whenever you provide the pointer to free, we consider it just successful. It should be successful all the time, 100% cases. 100% of the time, the invocation of the free should be successful. In more detail, what exactly type of this size? So it depends on the architecture that you're gonna work on, but we typically say this is a size type. So when we say size type, it depends on the architecture again. For example, if you're working on 64-bit architecture, it represents the unsigned long, which means the unsigned integer representation of the architecture. In this case, 64-bit unsigned integer, or unsigned long, for instance. If you're talking about x86 32-bit architecture, it basically say an unsigned integer, in this case 62-bit representation of unsigned integer. In fact, there are other similar type of size like signed size, but in fact they're getting the size representation as an argument, basically indicate the size of the memory that you want to have as a return value of the malloc. So what's the type of pointer? It's a general purpose type, so it's actually return void start. So if you want, you have to cast this one for your own type. For example, you provide the size of the struct to the malloc, and once you have this sequence of byte, the memory region, you're gonna cast this region into type. For example, the struct type that you allocated in the first place. So these are definition or API of heap allocator. So there are interesting questions. What if we provide malloc with 0 value? What will be the return value? It doesn't make sense to have 0 value, or it doesn't make sense to have 0 size memory region that I require. But this is kind of philosophical debate whether we should just return null to indicate the error value of the malloc. So whenever malloc fail, there's a chance that malloc fail. For example, you provide much more size than your virtual memory space or free regions in your process, it should fail. So in order to indicate the value, it will return null value. But this is pretty interesting because as a user, they request a 0 size memory region. But if you see the behavior of ptmalloc, which is a malloc of libc, GNU libc, they all return a certain object. So in fact, they never return null. In fact, they allocate the zero size object and then return the pointer. The reason behind this is that there is a common API usage pattern that once you allocate certain region based on the request, you're gonna reallocate it, not limited to these two API. In fact, there's many other API, realloc and calloc and etc. for other purposes. So in order to in order to make sure the pointer value can be reallocated, they tend to return a object value as a result, even if a user provides the zero value. So it's not null as a result. What about we provide malloc with -1? This is another interesting parameter because the size value here is unsigned integer representation. So but what if we provide the -1? So -1 is unsigned integer representation, as you saw in previous challenge. It is all 1, which means FFFF with the architecture side, right? If that's the case, if you have ridiculously large virtual address space, you should be able to allocate this, right? But unfortunately, as a kind of conventions and behavior, there's a limit of the size. We typically consider max size is less than half of the size t value that we can represent through those type. So this value will be rejected and return null. So maximum size you can allocate is a maximum size value and half of them. If you can provide them, malloc will really allocate that large memory and return for you. So another question, if we provide, say we provide the correct size value and we got the pointer, what's inside this pointer value? So without doing anything on this pointer, we happen to access this region. It also depends on the condition. Apparently it's not 0 in most cases. It also depends on how the process utilizes memory region in the past. If the object region happened to be free in the past, likely contains some of the interesting data pointer that represent the heap space of the process. If that happened to be a newly allocated memory region, likely this contains 0 value as a result. And these are the places that we're gonna leverage in terms of code pointer leak or in terms of exploiting the heap vulnerability that we're going to talk about in next week. In terms of free, there were also many interesting questions. Say that, what if we provide free with no value? Right? When we don't have any return value, what's going to happen? In fact, nothing happened because this is also another interesting convention a lot of developers are utilizing. So that otherwise, whenever, for example, let's say free only accept some of the value pointer. If that's the case, you potentially you need an extra branch to handle the null cases of the pointer that you're going to pass to the free, depending on the state of the object you like to free. So by having this convention, in fact, it drastically help in terms of writing error handling routines in C program, so that in case the object is already free, it happened to be a null operations. So this basically will be ignored. And what about we provide free to the pointer, and then is the pointer going to be null? In fact, it's not. It contains the original value as it is. So the library never set the pointer to null as a result. So because of those reasons, a lot of people tend to put the additional null assignment after free, depending on the usage of this pointer. But if you happen to access the pointer after free, it becomes very serious vulnerability that we're going to discuss about next week. So what if we access the free the pointer because it is not known? What if we access this? In fact, if you access those pointer after free, again, this becomes a very serious vulnerability, and depending on the context of the free, you can likely access some of the metadata of the heap allocator. Or sometimes, if you are a multi-threaded application that happen to allocate another chunk in the other thread, this pointer point to a legitimate memory region the another thread want to execute. So if something happened in the middle, say additional malloc happened because the pointer memory space is reused, in fact you can access the correctly allocated memory region through this pointer. What if your allocated memory region contain a code pointer and you have access to those memory region through this already free pointer? In fact, this become a very serious vulnerability and exploitation technique that we can launch together. Okay, so easy. Let's write it down here. There are a few goals of heap allocator. Apparently, the performance is one of the important criteria. So when we say performance, it's performance of malloc or the operations of malloc or operation of the free. So two other aspects you can think about when we're talking about performance of heap allocator. And the second goal, I'll say fragmentation. It's also known as memory utilization, right? Particularly in the all good day, we have a limited virtual space. So the fragmentation is one of the very important subject in, I would say, last 20 or 30 years ago. Last 30 years. But in modern computing environment, that we tend to have a lot of DRAM and virtual address space. It becomes less and less important. But many of the heap allocator, modern heap allocators, still really focus on reducing the fragmentation issue. In other words, they really hard. They work really hard to increase memory utilization of the limited virtual address space. The last goal of the malloc or heap allocator is what we call security. Similar to what we've been seeing so far, overflow of heap objects still exists. For example, you allocated 2 sequences of object, you overflow access of the certain object to the next one. And another interesting vulnerability that I described before is what we call use after free. So we're going to talk about this type of vulnerability later, but basically you access the memory after free the regions through the pointer that you already have. And again, in the meanwhile, there is a chance that other people or same code as well can allocate or can start using this memory region, so that through the dangling pointer you now have access to the memory region that other thread or my certain part of my code considered as integral. Right. Through this type of security features, this type of security vulnerability is one of the great consideration in modern heap allocator as well. Considering these three different goals, let me show you how we can actually allocate. Let me actually implement the heap allocator. So the very first heap allocator that we're going to implement, what we call very simple design, very fast, and very secure. Perhaps this is one of the most secure implementation of the heap allocator. So basic idea here is that when we invoke this malloc, we're going to replace this malloc code with mmap. Say you request a malloc with certain size, we just invoke the system call of mmap with the size parameter. Then operating system allocate enough chunk, in this case a page, that contain this size value. Say you provide 10 bytes as a malloc core, the mmap will return a page-wide memory region. Say typically the page size is 4K, so you will get this 4K region as a result. What about free? Given a pointer, we simply replace this API call with mmap. So as a result, we simply deallocated this memory region by invoking a system call, what we call mmap. What's interesting here is how it behaves. For example, because of mmap likely allocate a page worth of regions in the random places in the heap space. Say this is a pointer, and if you allocate another region, you're gonna have another page worth of memory region allocated in a separate space in the memory. So think about security issue. For example, say even if you allocated one page, your request size is smaller than this guy, right? So that you have enough space, but because of alignment requirement of the page, you ended up having more space as a result. If you have a buffer overflow that's slightly beyond but within the page, there is no effect because your allocator nicely handled the situation or happened to handle the situation for you. What if we ended up overriding more and more and beyond the page boundary? Because this particular region is not correctly mapped by the operating system, so you will get the segmentation fault. The program will stop immediately. So it's kind of interesting fact that between these allocated memory page or memory region, we have some of the interesting zone, typically what we call red zone, between the object. So every object tend to have zone in before and after, so that any sequential write on the buffer will trigger a segmentation fault that the system will stop. The process will stop immediately. What about user after free? So if we free this memory region, it immediately reclaimed by the operating system, so that whenever you access those memory regions through the dangling pointer, it also incur and this suddenly become a red zone immediately after this mmap. So if we access this memory region, the free memory region through pointer, you will also get the segmentation fault, so the program will stop. So it's pretty interesting that in terms of security, this seems like really address most of the security issue that we are worrying about. So it's a pretty good security features. It's pretty good in terms of security, and overflow is pretty good at handling this overflow. If overflow within the object, within the page, there's no effect. If you go beyond, it will be prevented. Right? It's a very good security features. But in terms of performance, it's extremely bad. For example, whenever we invoke the malloc and free, you ended up invoking one system call, particularly the system call of mmap and mmap require a lot of hardware interaction. For example, you have to modify the page font, and also as a result on a page table, and as a result you have to flush the TLB, and particularly in the many core operating system, you have to coordinate all these TLB flush across all the cores in your system. In fact, this is extremely slow operations. So and whenever you need a 8-byte chunk of memory, and you allocate through the malloc and mmap memory map, then your program will be extremely slow. So in terms of it, really bad, but in terms of security, it's pretty good. What about fragmentation? In terms of fragmentation, we have to think about two different kind of fragmentations, what we call internal fragmentation, and external fragmentation. So when we say internal, this is what we meant. Given a one allocated page, in fact, we are using a small part of the region. And this is the only valid bit. We're going to waste it, this memory region, right? So if we see unutilized memory region within the object, what we call this internal fragmentation. So in this scheme, internal fragmentation is really bad. But what about external fragmentation? Assuming this is one unit of allocation, right? So whenever you free it, immediately free to the systems, and this entire memory region will be considered as a one sequential, one contiguous free memory region. If you as a program request more memory, then in fact they can pick up the memory region that cover all this memory region for you. And all the fragmentation issue, external fragmentation issue, will handled by the operating system. So in that sense, it tend to have very good external fragmentation handling as a result. So, but why we cannot use this scheme? Like, whole purpose of malloc is about performance. So it's really not about the security and fragmentation, but it doesn't do its job. Although it's a very simple scheme and fast and secure, but unfortunately it's not usable, because the whole purpose of malloc is to avoid the system call underneath, so that we can avoid the unnecessary system call, but still we can maintain this object in the application. The second design, so that we're going to talk about, is that we like to propose a scheme to avoid the system call whenever we invoke a malloc and free. So let's delete this guy. Say this is a simple and very fast allocator. So second design that I like to show you is what we call simple and very fast allocator. In order to do this, let's consider this situation. Say that we invoke the malloc with the size parameter 1, and as a result, it will return pointer value 1. And then we're going to do another malloc, say size parameter 2, and return another pointer 2. And then say we free the right before previous one, like pointer 2, and say malloc once more. So you will get the pointer. So if you see the heap space, say this is one big heap space, and this is the beginning of the heap. So in order to support these fast operations, fast allocations and free, we're going to introduce one global metadata, say global pointer, that indicate the beginning of the free heap region. So when system boot up, we allocate the gigantic heap space through the one big mmap call, and then we're gonna divide this one into smaller chunk. So again, when process boots up or launch, you're gonna invoke a mmap, so that you're gonna allocate large chunk, and then whenever application invoke malloc, so we're gonna divide the small chunk and return back to the application. So G pointer initially pointing to the beginning of the heap region, say global pointer. So this is the beginning of the heap region. Say if we allocate size 1, if we get the request of the size 1 allocation, we simply proceed the global pointer, simply return the pointer that pointed by G pointer, and proceed this one with the size 1 value. So now we have another updated global pointer that pointing to the free heap space. All these regions are free, but this is what we just return, right? So whenever we got another malloc, we're gonna proceed the global pointer to say size 2, and then we're gonna return this memory region to the outside. What about free? Because our goal is to make a fastest allocator, is to design fastest allocator, in fact we can ignore free completely. So whenever we free, we just ignore, right? It's completely fine because there's no requirement of the free in terms of API. We can behave that whenever a malloc is successful, we can make sure every free is successful, right? Because we just ignore them. And no one will be reusing this memory region too. So in terms of security, it's a pretty good decision too. So if you get another malloc request, we just proceed as if nothing happened in terms of free. Increase the global pointer by another size, and we simply return the pointer that pointing to this memory region. So it's pretty easy, right? So in terms of implementation, it's extremely easy. Say, given a malloc of the size, in fact, what we are doing is that we just keep the pointer from the global pointer, and we just gonna increase the global pointer by the size that user is requesting, and just return the pointer. What about free? So given a pointer that we correctly allocated from the malloc API, we does nothing, right? So in terms of performance, is it good? In fact, malloc performance requires just 3 instructions, maybe 2 instructions. So extremely fast. What about free? It's a knob. It can be faster than this, right? So extremely good performance in terms of malloc, extremely good performance in terms of free. What about security? What about user after free? In fact, there's no free in these operations because we ignore. No one is going to reuse the free memory region. In this case, this particular one, right? When we invoke this free. In fact, although even if you have a dangling pointer, it's completely fine to access because no one will be accessing this memory region, or no one will reuse this memory region for legitimate purpose. So in other words, it actually make the UAF definition obsolete because there's no free, in fact, in this allocation scheme. So in terms of security, it's extremely good. You can basically eliminate a single class of vulnerability that modern applications are suffering from now. But what about overflow? This is a pretty interesting one. For example, similar to the buffer overflow, say this second memory region is allocated, that in fact you can override the another memory region next to you, right? That's pretty unfortunate. But interestingly, if this object is surrounded by this free region, maybe 1 byte override perhaps can be mitigated because the free memory region might exist right next to you. So this is interesting, but still is pretty vulnerable, right? What about fragmentation? So in terms of internal fragmentation, in fact, there is no issue because whenever we allocate, we're gonna very precisely allocate the memory region required for the size. For the external fragmentation, it's really problematic because we are not reusing these memory regions, right? So this is really bad, unfortunately. The next allocator we're going to talk about is to improve the fragmentation. So far we've been seeing a very simple and clean design with very secure allocator. In fact, whenever you invoke malloc, we just invoke mmap. Whenever application invoke free, we just invoke mmap. So this seems to be very interesting design, but suffer from performance. So that in other extreme, we now propose a fastest possible design in terms of allocator. So in those cases, we only maintain a global pointer as a global metadata, so that we can keep increasing those pointer and return the corresponding pointer back to the user. Not only that, what's interesting is when user invoke free, in fact we just ignore, so that we can even enhance the security concern that we have while we call user after free. But unfortunately, this scheme suffering from external fragmentation, which we like to solve in next iteration of the design. Say, oops. So one good way to solve these fragmentations, instead of discarding this free memory region, we like to use so reusable allocator. So we like to use all the free chunk when we are malloc, when we are processing malloc. So in order to do this, we like to introduce another global metadata, what we call free list. So this is nothing but a list of the free chunk. It basically contains a list of the free chunk. For example, when we execute these free operations, right? So we're gonna, instead of discarding this pointer, we're gonna put into the free list, say pointer 2, right? So that the free operations is not become just nope operations, but rather we're gonna print to the free list. Say append. So basic idea here is that instead of discarding the free memory regions, we're gonna keep track of them on the free list, so that whenever necessary, we're gonna reuse them. That's a key idea. Then how can we implement this malloc? So instead of just returning, oh cool. So instead of just returning or increasing the space and return, what we're gonna do, we simply check all the free list. We're gonna just iterate the free list, say and see if the size parameter is nicely matched with the size of the free chunk, right? If that's the case, we pick one, we choose correct free chunk in the free list, so that we can just discard this pointer, say unlink, just say unlink. I'll link the pointer from the free list, and we're gonna return. So this is pretty interesting. What if we, let's say all the sizes here are same. So when we are free, so when we are executing this guy, now the free contains the pointer 2. Say this all size parameters are same. That unlike we are getting pointer 3 in the next malloc, if size 3 is equal to size 2, then while iterating the free list, we consider the previously allocated object in the free list is matched with the size parameter that we are requesting. If that's the case, pop the corresponding pointer from the free list and return to the user. So in fact, because of this free list in my system, now I can maintain, now we can reuse the memory in my heap, so that we can enhance the reusability of this fragmentation, so that we can address the fragmentation issue by having this method. But let's think about other metric. What about performance of malloc? Unlike previous one that we simply increase the global pointer with a couple of instructions, unfortunately we have to run the entire for loop. Is it bounded? Perhaps not. When we are talking about a browser or web server that tend to have a longer lifetime, you might hold a lot of free list, free chunk. So whenever you want to allocate it a new memory, then you have to iterate the entire free list to find the right one. And then again, the whole purpose of this malloc is to have faster allocation, but unfortunately, we now introduce a very weird behavior or performance glitch in the malloc. So, unlike the previous one, the performance of malloc is really bad. So what about free? So free, on the other hand, similar to the previous one, it basically append the pointer to the free list. So it's still pretty good, right? But unfortunately, only the problem is a free malloc. What about fragmentation? So it's slightly better. We still don't have any internal fragmentation, which is good. But we kind of have a good effort to reduce down the external fragmentation by reusing some of the memory region. So it's slightly better, but still it's not the ideal, right? It's just slightly better. So what about security? So unfortunately, because of this reusing behavior of allocator, in fact, this usually for the free vulnerability, become an issue. And similarly, overflow still exists, right? Previously, there's a little bit of a concern to override the free chunk, but in fact, now you can override, if the free chunk is reused after, there's an opportunity to override the another legitimate chunk through this method. So in terms of use of the free and buffer overflow, is pretty bad, right? But there's another caveat. So when we are iterating the free list, we naturally assume that we know. We naturally assume that there is a known parameter, what we call size of the previous chunk. But in fact, we can assume that there is a key value store that keep a pointer as a key, return the corresponding size as a result. But in fact, we are not actually recording this information, so that given a pointer, right, fetching this size parameter is extremely hard. Then how can you handle this situation? Again, you can get a separate database to keep track of them, but unfortunately that's not ideal. The one common method that people are implementing in modern heap allocator is to keep track of those size right before the object region. For example, in order to keep track of the size of the first object, we're gonna use one additional memory region right before my pointer, so that we're gonna keep track of this size parameter here. Similarly, we're gonna keep track of the size parameter of 2, the object 2 here. We're gonna keep track of the size parameter of the object 3 in these locations. And your global pointer might start might start here instead of these locations, right? Similarly for the other, all shift by a little bit. But your object still get the corresponding pointer that have enough size that you can use as a result. Size 1, and this is size 2, and this will be the size 3. So when we are iterating list, what we are doing, given a pointer, we're gonna subtract the pointer with the size of the integer value. In this case, say it's a 4. Then we're gonna just subtract this pointer by 4 and access the region. Then you will get the size. So when we are iterating the free list, basically given a pointer 2, when we are getting this malloc request, we starting from here, fetch the size value, and compare with the size parameter that we are requesting here. If that's match, we're gonna pick up this memory region and remove or unlink from the free list and start reusing this memory region as a result. So it's pretty cool, right? We now have a complete routine to keep track of them. Another interesting trick that we're gonna talk about right now is that what if there are multiple free objects? So let's think about the situation where we free once more. Free pointer 3. Okay. So in this case, the size parameter 2 and 3 are different. They happen to allocate the another one. So basically, you want to free this memory region here. So this is a free, so that your free list now have a pointer to this memory region, right? Then where can we maintain the linked list? In fact, again, you can have a separate database to keep track of their order, but in fact, this region is completely free. In other words, no one is using this memory region, so we know that. So as an allocator, we create a metadata inside the free object. So instead of putting nothing in here, we start utilizing or start leveraging the free region so that we can create another pointer from here to the next chunk. Here, a little bit hard to see. And because this is the last chunk, and we just free this memory region, we're gonna say this is null. So that on top of the free memory objects, we now have a list starting from the global variable called free list. We can start chasing them by using one of the memory cell inside the free object, so that we can chase the next one, right? So we now resolve how we iterate this free list. We now have a size parameter that we can look up from the pointer that we have. But this type of structure, what we call inline metadata, because we embed the metadata as part of the memory region. So this is a pretty interesting in terms of security as well. So far we've been discussing about UAF and overflow, but in fact there are many things you have to consider in this architecture, because now we have a lot of pointer inside the free region. So the very important problem, what we call unsafe unlink. So if you see these operations as part of malloc, right? Because of this unlinked structure, if there is overflow in the first object, you can now hijack the operations inside these free chunks. So this becomes a new type of issue in this allocator. Not only that, other data such as size. For example, if there is overflow in the object 1, you can override all the way down and start overriding this size parameter. In other words, you suddenly change the size parameter of the next chunk, which will become another serious issue. So overriding metadata. So this type of interesting issue will show up because of the feature that we introduced. Particularly, we like to reuse certain memory region to reduce the fragmentation. So it becomes a very bad security decision at the end, right? Is there anything that we can improve? We're still suffering from these two types: the performance of malloc and external fragmentations when we are dealing with the large chunk. So let's first talk about these malloc operations. Is there any way we can improve the performance of this for loop? So first of all, we're gonna iterate the entire free list. That's fine, but in fact, there's a small trick that you can think of. What if instead of we just pick the object that exactly match with what I'm requesting, what if we change this equal sign into less than the free chunk is bigger than what I'm requesting, or bigger than equal, that we're gonna pop from our free list and return. So if we are requesting size parameter 3 with the smaller value than size 2 or equal, then unlike the previous operations, we in fact pop this memory region and return back to the user. So we kind of improve this malloc operations in terms of performance a little bit. But unfortunately, because of this region, because of this behavior, we now introduce, or now we are compromising the internal fragmentation a little bit. Now think about this situation. Say so previously we free this second chunk, and that was existing in the free list. But when we are requesting malloc, because the malloc, the size of size 3, the size of the third object is less than the size 2, meaning that we're gonna just return this memory region, right? But as a program, we only gonna utilize the smaller than the usable size. In this case, a size of 3 here. And this memory region will be discarded. No one will use this memory region. So we assume that the object is allocated from here to here, the original size of the object 2. But in reality, when we are getting the object of the pointer of the object 3, we're gonna only utilize the memory region starting from here, the size parameter 3. Because of this interesting inequality sign in the malloc. This is cool, but we're suffering from internal fragmentation now, because we start having some of the memory region which happen to be included as part of the allocated memory region, but in fact is not utilized well in this scheme. So how can we avoid this situation? So in order to solve this, we like to introduce another feature, say handling fragmentation. So we're gonna think about two approaches, like the approach for internal fragmentation and approach for external fragmentations. So in order to handle this, the one cute idea that we have is that instead of just discarding the what if, we're gonna push this memory region again to the free list. For example, after this malloc operation here, so instead of having pointer 2, we're gonna have pointer 2 dash, that pointing to here. Perhaps point to here, say pointer 2 dash. Right? But here, in order to make it as a malloc structure, malloc chunk, we have to put the size value of the pointer 2, right? Pointer 2 dash. In this case, we can put the size value to minus the what we are using in the size of 3 minus the size of the this additional metadata. Let's write down once more size parameter. Okay. So this is a new size parameter, but in this case, because we divide this size 2 chunk into 2, so we're gonna reduce down this size requirement by size 3 that we're gonna use in the upfront, and the size of this one metadata that represents the size, and this basically represents the size from here to here, and we're gonna push this pointer 2 inside the free list now, and this parameter should be updated as well. So instead of having size 2, we can put it as a size 3. So now we respect the structure of the free chunk, and free list now pointing to this memory region. If we have additional malloc request that is less than size this particular size, there's an opportunity that you can utilize and integrate the remaining part of the second object. So basic strategy of handling this internal fragmentation, what we call split and reuse. So we split this memory chunk and reuse the remaining chunk by pushing it to the free chunk. So this is a pretty interesting way to maintain, address the internal fragmentation, right? So implementation of this issue is also very simple. So basically, given this malloc request, you can do additional sign-list operations in the middle. How can you handle this external fragmentation? So we're going to talk about two approaches, what we call forward consolidations and backward consolidation. The basic idea here is that whenever we see two consecutive free chunks, we're going to merge it together. So let's say in this example, and say size 2 is free and size 3 is free as well. At the moment that we free the next chunk, say we don't have this guy, and size 2 and size 3 exists in here and here, and this is a free before that exists in the free list, and this is also free and that exists in the free list as well. But at the moment that we're gonna see the free request, when we are processing the free request of the object 3, we like to check whether previous object is also free or not. If that's the case, we're gonna merge these two chunks into one. The basic idea here is that you can just discard this memory structure and then simply add it to here. So in structure manner, in terms of malloc structure, instead of having two free chunk, we have a large single chunk, and their size is represented from here to here. So unlike previous cases that we couldn't handle this external fragmentation because we merge multiple free chunk into single, so there is opportunity that we can handle larger chunk requests in malloc because of this behavior. Right? This is a pretty interesting because in terms of free, we now have additional operations that we have to do. So basically, instead of having this instead of just pushing the pointer to the free list, what we're gonna do is to give a pointer to the new chunk. If previous object of the pointer is free, then we're gonna merge my object to the previous one. And also, if next object is also free, we're gonna merge myself into the next one. And because of this rule, we now have a very interesting property that we are maintaining as part of the heap space. So because whenever we see the opportunity, then we're gonna merge it together. So in other words, whenever we're free, we kind of check the previous one and next one, and sometimes we merge back and forth together, right? If there's a two free regions and here, then we merge into the forward, merge onto the backward. So because of this region, if you took a snapshot of the memory region, there is no consecutive free list. For example, there is no such a case that you see two sequential consecutive free chunk allocated in the heap region. because of the routine, two free chunks should be always merged together. So because of this property again, all the free chunk before should be the allocated chunk, or the chunk after also allocated chunk as well, because of this property or invariant that we are maintaining as part of the free. So this is particularly interesting because once gain a pointer to the allocated chunk, there's opportunity to overwrite the free. Whenever you have access to the free, you can always overwrite the allocated chunk right after, right? So this is a pretty interesting way to think about the integrity of the heap space. But how can you implement this prev and next? This is a pretty interesting operation. Given a pointer, we like to find out the pointer of the previous chunk, which locate right before myself. In fact, it can be done by iterating free list. For example, given all the free chunk, say pointer 2 and pointer 3, just iterating all the pointer in the free chunk, because we know the size of this corresponding pointer 2 and pointer 3, we're going to simply add up the pointer 2 with the pointer 2 size and pointer 3 with the pointer 3 size, and see if this is exactly same as the pointer that we are freeing. So if we can find those, right, then we can say this pointer exists in the free. So previous chunk is free, so that we can merge it together. For the next one, we're gonna iterate together, but we're gonna do the computation with the pointer myself from the size. So that given this value, see if such value exists in this list. So that if we can ever locate a pointer that matches with this size parameter, we can say the next object is a free as well. So that we can kind of perform this free by having this routine, right? And also this particular algorithm can be implemented pretty easily as a part of this. For example, let's delete. So if we identify the size is less than the requested size, or the size of the free chunk is bigger than the requested size, what we can do, move this code a little bit. So we're gonna keep track of the remaining size, say RSG, and the size of the original free, and size of the corresponding the requested size. And these are the size that we're gonna push back to the free list, right? First, so given this pointer, we compute its size. The original size is size 2 from here to here. The remaining size is after we subtracting this region, the size parameter. So basically this is the region, right? So first thing we're gonna do, once we have this pointer, say another pointer pointing starting from here to the size that we're requesting, and plus 4. This is metadata, so we can skip here. The pointer is now pointing to here. First thing we're gonna do is the pointer, update the request of the size of the new chunk, the remaining chunk. So that we're gonna update with the size value. In fact, this is not the entire space. We have to subtract this guy again. So this is this will be updated with the corresponding chunk, and then we have to update this chunk as well, right? So that we're gonna update with the size parameter they're requesting, and then we're gonna unlink. We're gonna unlink the P from the list, but at the same time we're gonna push back. We're gonna append the free list, this new pointer to the free list, right? If you perform this, the big chunk will be removed from the free list. We're gonna update this to metadata accordingly, and now free list will contain this value as a result. So it seems it's pretty doable, right? But there's one caveat. So in terms of performance, malloc operation is slightly enhanced, but not drastically. Still just minus. But what about free? The free operation was so simple, but we have to do all the consolidation in free, the forward and backward consolidation in free. And whenever we want to consolidation, we have to iterate the entire free list to figure out the previous pointer is free or not, or next pointer is free, or next chunk is free or not. So this suddenly become very bad, right? Unlike we wish. But in terms of internal fragmentation, we handle very nice. In terms of external fragmentation, unlike previous one, because we consolidate two free chunks together, so we now have one large chunk. So it become enhanced. So in terms of security, become worse and worse because there are more integrity that we can violate as an attacker. So unlike previous one, now whenever you do the free, there's an opportunity that you can hijack. Whenever you override the pointer, whenever you have an overflow in the legitimate chunk, there is an opportunity to override the metadata of the free, but whenever metadata of the legitimate chunk next to me. But whenever someone attempt to free, there's an opportunity that you can manipulate this code routine. So we're gonna talk about this. The details of this exploitation technique is in the next lecture. So given this setting, is there any way to improve the performance of free? A way to identify or a way to determine the status of the free and next chunk? So in order to do this, we're going to expand the idea of inline metadata a little more aggressively. So let me show you how we can do. Let's redraw. Say, so let me show you better handling of fragmentation. So let's say we have this code and 3 and size 4. So whenever we free, instead of putting the entire stuff in the free list, so what we're gonna do is to maintain the size of the free chunk. The reason that we couldn't look up immediately access the previous chunk is the fact that, so starting from here, given a pointer 2, pointer 3, we couldn't figure it out quickly enough the pointer to the previous chunk. So think about in the perspective of the pointer 3, pointer 2. We know the my size so that I can look up the next chunk. So in terms of this way, in this direction, we can keep chasing, so figure it out whether we can keep enumerate the size next to me. But in terms of forward behavior, so we couldn't locate the previous chunk given this information only. So we're gonna keep track of additional metadata, what we call previous size. So whenever this object is free, right? So we're gonna utilize this first region of the memory to keep track of the free list. So we're gonna use this pointer, this region as well. But at the same time, we like to utilize the last fields of the memory region. So we're gonna put my size, in this case, size 2. So one effect of this is that given this pointer, we can look up the previous size and calculate the next pointer pointing to the previous object. But in order to indicate the status of this entire memory region, we're going to utilize another bit field in the size. Say this is a previous in use. So whenever previous in use indicate 1, meaning that the previous chunk is free. In other words, the fields right before the size field is legitimate as well. So whenever we see p is equal to 1, so previous in use, then we can look up the previous size parameter of the free chunk, and then start enumerating, or you can just compute this pointer 2 minus size 2 and minus this chunk, and you will get this pointer 2, right? It's a simple arithmetic. So now because of this behavior, so whenever we see we have an indication of the previous chunk state in my size, we can actually iterate it to the previous chunk, which is enough for implementing this feature very quick enough. This one is pretty easy, because given this pointer, we're gonna calculate the next size by adding up this size value, but we still don't know the status of this object. So in order to go further, in order to figure it out the state, we're gonna chase one more, and then see if the previous in use of the next chunk, which indicate the free status of this next chunk. So by having this method, we can now quickly implement this next. We can quickly look up the previous chunk as well. Why we can put this extra metadata at the end of the size? Because all the object will be nicely aligned within the malloc structure. So another big reason is that because we like to utilize the free chunk as well. In fact, at least in this current structure, there's two fields that we are utilizing. For example, in 32-bit architecture, this field will be 4, and the size field will be 4. So in other words, whenever we got the malloc request, we're gonna make sure that at least this object will contain 8 bytes of the region, so that whenever necessary, we can utilize those two fields in the free memory region. Right. So this is a common requirement of the modern malloc as well. So typically require, in fact, in real ptmalloc implementation, they're not just using this one field, and 4 different fields they're utilizing for doubly linked list and even skip list, depending on the type of the free structure. So this become a minimum alignment requirement of the free structure, and given this, because we have this property and alignment requirement, the least significant bit of the size will be discarded always, will be always 0, right? So whenever we access the size fields, we just mask out those fields and compute the corresponding size of the chunk as well. So this is an additional bit that we are maintaining. Say if we discard 3 bits, so align by 8, then we're gonna have 2 additional bits that we can utilize for other property of the free. In fact, in modern allocator, they also allocated this chunk is really from this normal small chunk, or Mmap-based, or main arena or not. So main arena basically indicate a global heap space. In fact, if one user can create another arena that contain a different type of the heap chunk if they want. For example, different thread will allocate their structure, their memory objects inside the separate arena, for instance. And in fact, this kind of follow the exact form of the ptmalloc that you're gonna see as part of these challenges. But in terms of ptmalloc, in fact, they really have more complex optimization technique. I like to give a little bit of hint upon those operations, those optimization technique as well. So one thing that we are not happy with in this design is this malloc operations. So it seems we kind of address this internal and external fragmentations, and performance of free now become very fast, right? Unlike the other. And we still have a big problem in the security. Well, in fact, we have a more problem because we now have a more complex structure like previous size and etc. This become all interesting attack vector that we're gonna discuss in the next lecture. But is there any way to improve the performance of malloc? So basically, is there any way to avoid the iteration of the free? In fact, these operations are just single constant operations, but free iterating fully list seems like still too much. So in order to do this, the modern allocator, instead of having this one single list, discard this. So instead of having one free list, in fact, modern allocator has a multiple free list as a global structure. Sometimes we call binning. So given a one bin, instead of maintaining a single free list, we're gonna divide the free list by size. Say the first element of the free list indicate the size object from say 8 to 16 and 16 to 32, 4, and etc. So this one is basically performed as a free list. Say if there's nothing, just nil, right? One nice thing about this, if say we got a request of malloc with size parameter 6 or 18, right? Then we can just pick up. We can just pick up based on this bucketing node. We're gonna map this one into bucket size. In this case, 32, and this nicely fit into the 32 or 32. We're gonna pick up one element from here and return. Say there is a one free list here. Right? Just pop the element in here and adjust a little bit and return, right? If there is no such element, say this is empty, then we can go for the next one, all the way to the constant size of this table. So it has say 32 different kinds of bucket free list in one bin. Then we're gonna pick any of the element that bigger than the bucket size of the requested size. So in most cases, you can make a constant operation for picking one element out of the free list by having this tree. Not only that, in terms of modern PT malloc, we are not just having this one free list. This is typically called fast bin. But not limited to fast bin, we have small bin. We also have large bin. Nowadays we have a TC, Tcache as well. So basically all these binning structure now have opportunity to optimize this free list. So all these have a different property. For example, in the free list, we are not gonna handle this internal fragmentation. So whenever you guys see this, pop and return. So although we're gonna return for the 18 size request, we're gonna pick say 32 bits, and there will be additional unused area for the smaller size. But like that's okay because it's small enough that whenever we push back, it will be in the free list, right? So for those, we are not gonna handle this. But for the larger size, we have a small bin structure. So similar to this fast bin structure, we have much larger range, but in this case, we're gonna maintain this doubly link. The main reason behind this is that it's not worthwhile to perform consolidation on the free list, but in fact, we want to do consolidation in the smaller bins. But in other words, we now have two separate data structure tracking their relationship, right? But given this chunk and this chunk, say chunk 1 and chunk 2, if we want to consolidate each other, once we identify this through this metadata that we created, we can locate this guy and merge it together. But at the same time, you have to iterate this chunk and looking for the right order and eliminate this one from the free list, which is unnecessarily performance heavy. So in order to avoid this, we now introduce this doubly link, so that whenever we obtain the previous chunk, by using this doubly link structure, so we can, without iterating the entire list, we're gonna discard them. So in this type of structure that we call fast bin structure, it's impossible to implement this in the faster manner, right? Because it's always required to iterate from the binning structure of the size, looking for the corresponding element, so that any element that pointing to the consolidated one should be discarded in the fast bin structure. And this is the current optimization that most of the modern heap allocator have. And again, depending on the property, you should think about how to attack them as well. In fact, there's one more, like unsorted link as well. So all these structure will be you can find from the actual implementation of ptmalloc. So as a last topic, I'd like to quickly highlight some of the security problem in this domain. Sure. So the first security problem is what we call use after free. We often we've been calling this as UAF. So whenever you free the object, right, and you access this pointer, what's in here? First, there's a potential opportunity that other objects is allocated in this structure, right? In those cases, you're attacking the application's behavior that might contain some of the function pointer in virtual table, right? And in terms of heap allocator, whenever you access the pointer, you now have an opportunity to craft one of the metadata of the heap space. Again, as we learned from the previous topic, whenever things are free, the first area will point to the next chunk, right? If you read this by accessing them, then you're gonna now decipher the memory address regions of the heap space, even if it's randomized, because we know likely the pointer will contain the next free chunk in the system, and you will get the data pointer out of this execution. Another one is double free. So basically, you free the pointer one time, another free. Think about the binning structure. Say this is the correct bucket of the freed object. So insert it one time. So in other words, because you now have a the free object is inserted to the same bin. So if someone is requesting the size of the pointer and another malloc invocation, and the return value of the two malloc will be same because of the double free. In other words, if attacker obtain one of the value, then start overriding them, and another part of the program consider the allocated chunk is integral, but unfortunately we can override those by having this method. Another simple one that we've been discussing is overflow. Basically, if you say in this memory region, now we have a multiple data structure you can override. So starting from here, say this is a, let me draw. So say there's overflow here, say this is the allocated chunk, then there's an opportunity that you can override the size value. Not only that, there's an opportunity to override this previous in use bit, right? Previously is not used because it's allocated, because I'm using right now. But suddenly, by overriding one value, is a previous in use, say 1 indicate that the previous chunk is allocated, say is originally 1, but if you override with the 0 value, suddenly my allocation region will be considered as a free. So in this case, so allocated region, because of the overflow, now this chunk will be considered as a free by the heap allocator. What if we free this new chunk, the pointer? Because now we consider the previous chunk is free, we try to consolidate them with the previous one. But interestingly, there's an outstanding pointer pointing to here that program is still using. And once you free and allocate it again, then you will have the overlapping chunk with the existing pointer in the system. Right? This type of problem happen all the time. But interestingly, if there is one null byte, one zero byte over one byte, and zero override on the memory, then you will get this interesting behavior. So even if there is one seemingly benign overflow in the heap region, because of the integrity of invariant of the metadata, invariant of the heap allocator, in terms of heap structure, there's an opportunity that you can launch the exploitation against them. And this is all for today. If you have any other questions, this is a great time to ask as well.